Hello all, welcome to this video on system software. Today I'll be talking about assemblers. Let us begin by looking into the history of assembly language. The first assembly language was developed in 1947 by Kathleen Booth for the ARC2 or Automatic Relay Computer at Beck, University of London. This implementation resembles math to run a machine rather than the modern mnemonic form. The first mnemonic assembly language format was developed by Maurice Wilkes and David Wheeler for the electronic delay storage computer in 1949. SOAP or Symbolic Optimal Assembly Program was an assembly language for the IBM 650 computer written by Stan Polly in 1955. The modern implementation of assembly was developed in the 1960s for the IBM 7090. Several people like Douglas McIlroy and George Mealy worked on the project, which was called the Generalized Assembly System. Now let us see what an assembly language is. Assembly language is directly influenced by the instruction set and architecture of the processor. The assembly language code must be processed by a program in order to generate the machine language code. Assembler is the program that translates the assembly language code into the machine language. NASM or Netwide Assembler, MASM or Microsoft Assembler, and TASM or Borland Turbo Assembler are some of the popular assemblers. Now, why program in assembly language? There are two main reasons why programming is still done in the assembly language, the first being efficiency and the second being accessibility to system hardware. Efficiency refers to how good a program is in achieving a given objective. Here we consider two objectives based on space, which is space efficiency, and time, which is time efficiency. Space efficiency refers to the memory requirements of a program, that is the size of the executable code. Program A is said to be more space efficient if it takes less memory space than program B to perform the same task. Very often programs written in an assembly language tend to be more compact than those written in a high-level language. Time efficiency refers to the time taken to execute a program. A program that runs faster is said to be better from the time efficiency point of view. If crafted carefully, they tend to run faster than their high-level language counterparts. The other main reason for writing assembly language program is to have a direct control over system hardware. High-level languages on purpose provide a restricted or abstract view of the underlying hardware. Because of this, it is almost impossible to perform certain tasks that require access to the system hardware. For example, writing a device driver to a new scanner certainly requires programming in the assembly language. Since the assembly language does not impose any restrictions, you can have direct access over the system hardware. Now let us look into the applications. In time-critical applications, tasks have to be completed within a specific time period. These real-time applications include aircraft navigation systems, process control systems, robot control software, communication software, and target acquisition, for example, missile tracking software. Now looking into the accessibility to hardware applications. System software often requires direct control over the system hardware. Examples include operating systems, assemblers, compilers, linkers, loaders, device drivers, and network interfaces. For most systems, compactness of application code is not a major concern. However, in portable and handheld devices, code compactness is an important factor. Space efficiency is also important in spacecraft control systems. Now let us see some of the disadvantages of assembly language. First one being there is no symbolic name. You need to keep track of the exact memory location that a piece of data is stored. That is, you must manipulate memory locations directly. Second point is it's hard to read. Although we have made a few improvements by eliminating hex code, the command names are not always very clear. The third point is the code is still machine dependent. We haven't really moved that far away from the machine language, we have just put some pseudo-English labels on it. We still need to rewrite every piece of code for every machine. Fourth point being that it's hard to maintain and debug. Finding mistakes in machine code is difficult. Correcting them or adding new features can also be a challenge. This code must also be heavily documented. It's very difficult to figure out what a program does by reading the code. Detailed explanation must be prepared for future coders who need to modify or use the code. Now let us look into assemblers. Assemblers have been available since the 1950s as the first step above machine language and before high-level programming languages such as Fortran, Algol, COBOL, and Lisp. There have been also several classes of translators and semi-automatic code generators with properties similar to both assembly and high-level languages, with speed code as perhaps one of the better known examples. Next, we'll look into the different assembler design options. The first one being a 2-pass assembler with overlay structure. Then we have 1-pass assemblers and finally multi-pass assemblers. We'll begin with 2-pass assembler with overlay structure. Now, when there is a case when there is not enough memory, what we do is we'll share the available space with all the segments. That is, the available memory is divided into 3 segments. First segment will store the shared table and routines. The second segment will have pass 1 table and routines, and the third one will have pass 2 table and routines. This can be done because we know that pass 1 and pass 2 are never required at the same time. And these segments will be arranged in a tree-like structure. This way of programming is called as overlaying. So we can say that overlaying means it's a process of transferring a block of program code or other data into the main memory, replacing what is already stored there. Overlaying is a programming method that allows programs to be larger than the computer's main memory. Constructing an overlay program involves manually dividing a program into self-contained object code blocks called overlays or links, which are generally laid out in a tree structure. Sibling segments, those with the same depth level, share the same memory and are called overlay region or destination region. An overlay manager, either part of the OS or part of the overlay program, loads the required overlay from the external memory to its destination where it is needed. This may be automatic or done via explicit code. Often linkers provide support for overlays. Next, we'll look into 1-pass assemblers. Now, there are 2 ways of designing a 1-pass assembler. The first method is to produce object code directly in memory for immediate execution. This is done in load and go assemblers. No object code is written out here and there is no need for a loader. Now this is useful in program development and testing systems. Since programs are reassembled nearly every time they are run, the efficiency of the assembly program or the assembling process is an important consideration. Since object code is produced in memory rather than being written out to the secondary storage, handling forward reference is less difficult. Assembler simply generates object code instructions as it scans the source program. Now this code is the example of an SIC one-pass assembler. Now this contains the line numbers, location or addresses, in the source statement where we have the variables followed by opcode, operand, and finally the object code of each statement. And this is the same information with the same memory addresses, and this is the result of assembling process. Now if the instruction operand is a symbol that is not yet defined, then the operand address is omitted when the instruction is assembled. For example, if we take this case where we are encountering the operand rdirect, we see that it is not defined before it is used. It is only defined after its usage in line number 125. So we do not know the address in advance. So what happens is, the assembled code here will be missing because it doesn't know what the address of rdirect is. Rest, which is 48, will be present here. Now all the symbols which are used as an operand is entered into something called as a symbol table, which looks like this. It's entered only when it's encountered for the first time. And whichever entry doesn't have an address associated with it will be marked with a star. Also, whenever you get an indication about the address of a particular undefined symbol, it will be added as a list of forward references associated with that particular symbol table entry. Now, what is a forward reference? That is what I was talking about before. That is, usually what happens is, in this case, if we look up, for example, at the variable 0, we have defined it before actually using it in the program. So we already know the size and the address of that variable. But in the previous example, rdirect, what happens is, we are already using the variable, but it was defined somewhere later in the program. So that is called as forward reference. So what we see here is, whatever is added in the linked list is the address of that operand in this particular line. So this line number is 2012. The SIC format for an instruction will have 8 bits assigned to the opcode and 15 bits assigned to the operand address. So here what happens is, at location 2012 we have JSUB, the instruction. Then at location 2013 we'll have rdirect. So that is the value that is added as the list to this symbol table entry here. Now when the definition for that particular symbol is encountered, forward reference list for that symbol is scanned and proper address will be inserted into any instructions previously generated. If we look at the rest of the symbols here, we have the addresses readily available. If we look at the value 0, it is given as 1006, which is already available. If you look at the term first is 200F, which is also available here directly. Now at the end of the program, any sim tab entries marked with a star indicate undefined symbols, and they should be flagged by the assembler as errors. When the end of the program is encountered, the assembling process is complete. Now we look at the second type of one-pass assembler, which will produce the usual kind of object program for later execution. So when the definition of a symbol is encountered, the instructions that made the forward reference to that symbol may no longer be available in memory for a modification. They will already have been written out, or they will be part of a text record in that object program. So in this case, the assembler will have to write in a new text record with the correct operand address, so that when the program is loaded, this address will be inserted into the instructions by the action of the loader. We will see an example for that. We mentioned something called as a text record here. First of all, we will see what that is. Now the object program format will have three sections in it. The first one being the header record, where you have the program name, starting address and length. Then we have the text record, where the translated instruction and data of program together with indication of addresses where these are to be loaded are there. Finally, we have the end record, which marks the end of the object program, and they specify the address in program where execution is to begin. Now this is taken from the operand of program's end statement. Now this is an example of how the object program format is. Now we look into the details. Now the column names I am giving here, or the column numbers specified here, can change from assembler to assembler. This is with respect to the example we are discussing here. So looking at the header record, the first column will contain the letter H. Columns 2 to 7 will contain the program name. Columns 8 to 13 will contain starting address of the object program in hexadecimal, and column 14 to 19 will include length of the object program in bytes or hexadecimal. Next, we'll look into the text record, which will begin with capital T. Columns 2 to 7 will contain the starting address of object code in the record. In the record means in this particular line, which will be given in hex. Then columns 8 and 9 will include the length of the object code in this record in bytes, which is again in hex. And column 10 to 69 will contain the object code represented in hex, where 2 columns will be taken per byte of the object code. Finally, we have the end record, the first letter being capital E. Then columns 2 to 7 will contain the address of first executable instruction in the object program. Now this example is the same as the previous one we saw before. Now the only change that is there is, if you examine the previous assembled code, you can see that this term was not resolved because it was a forward reference. Now when you look at this, it is resolved, that corresponding address has been placed here. Now we are looking at the second type of unpassed assembler. So when you take this example, and we are examining the third text record, which is specifying that the value 2024 should be returned to the location 201C. So when that program is loaded, what happens is the value 2024 will be replaced by 0000. Now the other forward references in the program will also be handled in this way. The services of a loader are being used to complete forward references that could not be handled by the assembler. The object program records must be kept in their original order when they are presented to the loader. Finally, we will see the third type of assembler design, which is a multi-pass assembler. Now restrictions such as prohibiting forward reference in symbol definition, they are not normally a serious inconvenience for the programmer. As a matter of fact, such forward references tend to create difficulty for a person reading the program as well as for the assembler. Nevertheless, some assemblers are designed to eliminate the need for such restrictions. Now the general solution is a multi-pass assembler that can make as many passes as needed to process the definitions of symbols. It is not necessary for such an assembler to make more than 2 passes over the entire program. Instead, the portions of the program that involve forward reference in symbol definition are saved during pass 1. Additional passes through these stored definitions are made as the assembling progresses. This process is followed by a normal pass 2. Now the symbol definitions that involve forward references are stored in a symbol table. Now this table will also indicate which symbols are dependent on the value of others to facilitate symbol evaluation. Now let us see an example of how this is done. So in the example given here, we'll go through each line of code and see what are the changes that are updated into the table. So when coming across the first term, half SIC, we are given its definition as max length by 2. We'll enter both these into the table, max length and half SIC. Since max length is not defined anywhere, it is an undefined symbol, it's marked with an asterisk. Whereas we know the definition of half SIC, which is max length by 2, which is given here. This term &1 states that one symbol present in its definition is undefined. And this field is to show if any other variable depends upon this particular one. For the case of max length, we have half SIC which is dependent on it, followed by no one else, so that is marked as null. There are no one depending on half SIC, that's why this is null. Now moving on to the second instruction. We have 2 more entries into the table which are buffend and buffer. Both of these are undefined symbols, so they have asterisk marked. But they have a dependent variable which is max length, so that is given here. And we can have an updation on the definition of max length which was not defined previously. Now max length will be having a definition buffend minus buffer. Now we have &2 here because 2 symbols in the definition are undefined. Now we are examining the third instruction. We get 2 more entries. No, just 1 entry because buffer is already here. We get 1 more entry which is pref bet, whose definition is buffer minus 1. Again &1 because 1 symbol here is undefined. There are no one depending on pref vbt. So that is null. But when you update buffer, we see that buffer has both max length and pre-VBT dependent on it. So that is added to this list. And now we are assuming that the location counter contains a value 1034. So that address is to be stored as the value of buffer, which is 1034. Now we will check if any other value is dependent on buffer. We already saw that we have max length and PREVBT. So max length has 2 undefined symbols which cannot be solved right now. So we move to PREVBT. So PREVBT is buffer minus 1. So 1034 minus 1 is 1033. Next, we will examine any other symbols that can be resolved. Now suppose the value of buffend is defined as 2034. So using that we can resolve other values. So if buffend is 2034, we have buffend minus buffer, that is 2034 minus 1034, which is the value of max length, which is 1000. Now half SZ is max length by 2, that will be 500. Now next we look into the process of assembling. Assembling converts source program into object program if syntactically correct and generate an intermediate .obj file or module. It calculates the offset address for every data item in the data segment and every instruction in the code segment. A header is created which contains the incomplete address in front of the generated object module during the assembling, which we already saw in the form of object program format, where we had a header record, text record, and an int record. Assembler complains about the syntax errors, if any, and does not generate the object module. Now examining the process of assembling. We use an editor in the system to write the assembly program, which will be saved as program name.asm, which is given to the assembler for assembling. So which will generate the object code and two optional files, which is .lst and .crf. .lst is the listing file which has the entire offset map of the source file by including memory allotment, offset addresses, opcodes, labels for directives, and different labels and relocation information. The .crf file or cross-reference file is utilized for debugging the source program and contains the statistical information, size of the file in bytes, list of labels, number of labels, routines to be called, etc. regarding the source program. Then the obj file is sent to the linker for the process of linking. That will create the .exe file and two optional files, which are .lib and .map. Finally, the .exe file is loaded for execution by the loader. For short programs, assembling can be done manually, where the programmer translates each mnemonic into the machine language using a lookup table. Assembler reads each assembly instruction of a program as ASCII and translate them into the respective machine code. Lastly, we look into SIC and SIC-XE architecture. Now, SIC or Simplified Instructional Computer is a hypothetical computer system introduced in System Software, An Introduction to Systems Programming by Leland, Beck. Due to the fact that most modern microprocessors include subtle, complex functions for the purpose of efficiency, it can be difficult to learn systems programming using a real-world system. The simplified instructional computer solves this by abstracting away these complex behaviors in favor of an architecture that is clear and accessible for those wanting to learn systems programming. The SIC machine has basic addressing, storing most memory addresses in hexadecimal integer format. Similar to most modern computing systems, SIC architecture stores all data in binary and uses the 2's complement to represent negative values at the machine level. Memory storage in SIC contains of 8-bit bytes, and all memory addresses in SIC are byte addresses. There is also a more complicated machine built on top of SIC called Simplified Instruction Computer with extra equipment, or SIC/XE. The XE expansion of SIC adds a 48-bit floating point data type, an additional memory addressing mode, and extra memory, that is 1 megabyte instead of 32,768 bytes to the original machine. All SIC assembly code is upwards compatible with SIC-XE. That's all for now. Thank you for watching.